Welcome back to our first lesson after our exploration through the real number system. Today we pick up with an activity on scientific notation where we are learning to comprehend why the properties of exponents hold for positive integers, so I can generalize from repeated reasoning how exponent properties help us extend the definition of exponents from positive integers to all integers. I'll know I've got it when I can evaluate expressions with integer and rational exponents. On the right-hand side, we can see some of the vocabulary that you will have to define for this activity. So let's begin. If a is any real number and n is a positive integer, then don't know why that says exponent, because it's really supposed to say nth power is a to the n equals a times a times a times a certain amount of n factors. The number a is called the base, and n is known as the exponent. If the base is not equal to 0 and n is a positive integer, then we say that a to the 0 is equivalent to the number 1, and a to the negative n is equivalent to 1 over a to the n, which is what we define to be the reciprocal. For this slide, I ask that you define the exponent laws, since it's definitely something you've come across repeatedly during your time in Algebra 1, Geometry, and Algebra 2. For instance, in our first algebraic expression, when we are multiplying two bases with exponent values, we can simply keep one base and add the numerical exponents for what they are. Oops, that should be up there. Plus. Let's do some parentheses. There we go. Plus n. Keep it there. An example of this would be 2 to the third power times 2 to the seventh power. And you could definitely write all of those out. 2 times 2 times 2 times 2 times 2 7 times. And you'll get to the consensus that 2 to the 3 plus 7 is equal to 2 to the 10th. Okay. You do not have to be that thorough in your examples. Just this first piece of evidence, 2 to the third times 2 to the seventh, and that's equivalent to 2 to the 10th. So show me what you remember. Let's find out what you don't, and we can have a conversation about it tomorrow. In this slide, you'll kind of be putting into practice the definitions and rules that you had outlined on slide 3. Case in point, something like w to the 5th or raised to the third power would be what we call a quantity or a power to a power. So in this case, we'll multiply the value of the exponents. 5. And that will give us w to the 15th power. So that brings us to scientific notation, and it is imperative that we have a good sense of familiarity working with exponents, because scientific notation exclusively involves them. So scientists use exponential notation as a compact way of writing extremely large and extremely small numbers. An example of that would be the scientists over at NASA or those involved in space travel. The moon and our surrounding planets aren't necessarily a drive away. So in order to talk about those distances, rather than write out 15, 18, sometimes 30 plus zeros, it's easier to write things in scientific notation where there's common understanding that you're working with extremely large numbers. A positive number x is said to be written in scientific notation if it is expressed as x equals some value times 10 to the n, where the exponent is nothing more than an integer and this constant is a value between 1 and 10. Some words of wisdom: 10 to the 8th is a big number, so large numbers must get positive exponents, whereas 10 to the negative 5th is a small numbers, therefore small numbers must get, oops, not small, brain fart, negative exponents. Let's walk through one of these, since it could have been a significant amount of time. If we have this value of 1,750,000, the decimal point is currently located here. It is invisible since we are dealing with a value that is greater than 1. Okay? But if we were to relocate the decimal value, every time we move a place value to the left, back to our inaugural lesson on the number line in Unit 1, okay, this is the equivalent of multiplying by 10. So the number of times that we move or relocate the decimal value dictate the exponent. So if we're going to move the decimal 1, 2, 3, 4, 5, 6, the resulting number would be 1.75 times 10 to the 6th power, not 60. And as you can see, it's considered a large value, so the calculator does not indeed calculate it for you. But I'm sure if you went to Google software that will output larger values, you would see that the two numbers are identical. So for the remainder of this slide, make sure that you rewrite this next number in scientific notation while expanding those last two examples back to their numerical values. Now, what happens when we get to this idea of arithmetic in scientific notation? So when we're multiplying numbers in scientific notation, to multiply two numbers in scientific notation, multiply the numbers to the left, and I do not like that definition. So I'm going to say the constant terms of the powers of 10 and add the exponents of 10. You may have to rewrite to put the result in simplified scientific notation. And then once again, vice versa, if we're going to divide the numbers that are written in scientific notation, we can divide the numbers that are to the left, so those are our constants, and subtract the exponent of the tens. If you did not know that was an exponent law, I suggest you come back here and update your table accordingly. And then once again, you might have to rewrite to put the result in simplified scientific notation. So let's take a look at one of these examples. I will do letter B on the right side of our box. So I am dividing here, right? I have a fraction bar, and that I would divide the two constants. So 9 divided by 2 give me 4.5. And if you wanted to copy that multiplication symbol, you can press Control C on your Chromebook, Control V to paste, and now I'll have 10 to the negative 3 minus 5, because I am dividing, would yield a negative 8, and voila, we are done. The reason why I do not have to alter the structure of this constant is because there is a single numerical value to the left of our decimal point. Remember, our constant value must be a value that is between 1 and 10. And that is where we will conclude for this video, where we'll pick up with the enhancement opportunities in our next class.